This is Chapter 3, Part 2, Pre-Class Lecture. Chapter 3, of course, focusing on the radiation from the sun. And so in the last pre-class lecture, we talked about ultraviolet, also called UV radiation. And we learned there were three types: UVA, UVB, and UVC. UVA has the longest wavelength of the three, and therefore the smallest frequency and smallest energy. UVC has the shortest wavelength, and therefore the highest frequency and highest energy. UVB falls in the middle between those two. And so UVB and UVC radiation has enough energy to cause some molecular bonds to break. And so UVC photons that have wavelengths that are less than 242 nanometers can break bonds. And photons with wavelengths less than 320 nanometers, which fall into the UVB range, they can break apart ozone bonds. UVC radiation can break oxygen O2 bonds, and then we'll put another note here, and ozone O3 bonds. So UVC being stronger in energy than UVB, UVC can break bonds in both oxygen molecules, O2, and ozone molecules, O3, whereas UVB is only energetic enough to break the bonds in ozone. So why is it that UVB can only break the bonds in ozone O3 and not the bonds in oxygen O2? Well, we're going to be able to answer that question here shortly. So let's first take a look at ozone O3, since both UVB and UVC can break the bonds in ozone. Ozone, of course, has the formula O3. So here in this model, each of these brown spheres represents an oxygen atom. Ooh, excuse me. And so when ultraviolet light, whether UVB or UVC, they both are strong enough to break the bonds in ozone. So when that light hits a bond in ozone, and so the springs look like metal springs here, those represent what we'll call covalent, also called molecular bond. We learned about molecular compounds, and we learned how to name them and how to write the formulas for them. And we learned that molecular compounds, which are also called covalent compounds, contain only non-metal atoms. So ozone, containing 3 oxygen atoms, oxygen is a nonmetal, so ozone is a molecular or covalent compound, and therefore it has covalent or molecular bonds. And so when the ultraviolet light hits that covalent bond, it's going to first cause it to vibrate, and then it's going to cause it to break. And so that vibration, as more and more of the UV light is absorbed by the bond, the vibrations get stronger and stronger and stronger until the bond finally breaks. So when UV radiation is absorbed by our skin, and remember only UVA and UVB ultraviolet types of radiation actually reaches the Earth's surface, and therefore only those two types get absorbed by our skin. UVC is totally absorbed and destroyed in the ozone layer of the stratosphere. But UVA completely reaches the Earth, and a small portion of the UVB that's radiated by the sun reaches the Earth. And so when our skin absorbs UVA and UVB, the lower energy, longer wavelength UVA light has the ability to remove electrons from molecules like water in our skin. And that can create species that are called free radicals. So free radicals, they form when electrons are removed from molecules. And so those free radicals and other reactive oxygen species get formed. When electrons get removed from molecules like water. Now, UVB light is at a higher energy than UVA, and it's strong enough when it hits your skin to cause some chemical bonds to break in molecules like DNA. So DNA molecules are damaged by the free radicals that form when UVA radiation removes electrons from molecules like water. And DNA molecules are also damaged directly by UVB absorption, because UVB absorption has the ability to break the bonds in DNA. And therefore, this breaking of the bonds in the molecules will cause the release of a chemical in the skin called melanin. And it's a pigment that is brownish in color. So melanin is a chemical pigment that has a brownish color, and it's found in the skin. So when UVA and UVB radiation causes DNA molecules to be damaged, then the body will respond to try to repair the damaged skin, and it does so by releasing this brownish pigment called melanin, and that's what causes the brown spotting of sun-damaged skin. And this could result in cancerous cells forming and subsequently skin cancer. And so this picture shows that UVA, having a longer wavelength than UVB, it penetrates farther and deeper into the layers of the skin. It will penetrate the outermost layer, the epidermis, and also go down into the dermis and the subcutaneous layer of the skin. UVB, on the other hand, has the shorter wavelength between the two, and therefore it'll only penetrate the outermost epidermal layer of the skin. But because it has a higher energy, it can break bonds in DNA. So if I had to choose between UVA and UVB, if I had a choice of either one to be exposed to, I would choose to be exposed to UVA, because even though UVA penetrates deeper into the skin, its energy isn't as high as UVB. So therefore, it can cause some free radical formation, but it is not energetic enough to directly break bonds in DNA. And so if you're eating a diet that's high in antioxidants, you can remove the effects of free radical formation by being exposed to UVA. because the antioxidants that are in things like dark fruits and vegetables, like berries, those antioxidants will destroy those free radicals that are formed and remove them, and therefore prevent them from causing any DNA damage. So UVA is the less damaging overall to your skin versus UVB. Now, the UVC radiation is the highest in energy, and therefore, if it reached the Earth, it would destroy DNA molecules instantly. And so therefore, it's a good thing that this highly dangerous energetic type of UV radiation is absorbed completely by oxygen molecules in the stratosphere, preventing UVC from ever reaching the troposphere, which is where we live. So UVC is so dangerous that it causes the oxygen-oxygen bonds to break in both oxygen, O2, and ozone. UVB is partially absorbed in the stratosphere. However, some of it does reach the Earth's surface, and it's rapidly absorbed by the epidermal layer of your skin. And UVB can cause oxygen-oxygen bonds to break, but only in ozone and not in oxygen. UVA is not absorbed by the atmosphere at all. All of the UVA reaches the Earth's surface, but because it's not as energetic as UVB, it has a longer wavelength. It can penetrate deeper into the skin, and it causes more damage to the underlying tissue, like the dermal layer and the subcutaneous layers, as far as causing free radical formation. But it doesn't directly break DNA bonds like UVB. And so, some skin cancer facts. So we know that some good things about sunlight is, of course, it catalyzes photosynthesis, and it also provides vitamin D. But too much exposure to UV radiation can lead to cancers and also eye diseases. So most skin cancers are linked to exposure to sunlight. And so skin cancer can appear at any age, but it's more common in older people. The longer you've been on the planet, the longer you've been exposed and or overexposed to UV, the more likely you are to have skin cancer. And so skin cancer can develop after many years of repeated excessive exposure to sunlight. Even if you've stopped that excessive exposure at some point, still it can show up later on in life. UVA in sunlight at our Earth's surface is most strongly linked with skin cancers because of its deep penetration into layers of the skin, but UVB also plays a role because of its high energy impact on the skin and breaking of DNA bonds. And so therefore, you want to be exposed to UV radiation just enough to get the benefits of vitamin D. You don't want to have such low UV exposure that you have a vitamin D insufficiency, and even lower than that can even cause you to have some skeletal diseases if your vitamin D deficiency gets to be extreme. But you also don't want to be highly exposed to UV radiation so that you have skin cancer and eye disease risk. So you want to be at minimum risk and to have just enough exposure to sunlight to get adequate vitamin D, but not overexposure. So limiting the amount of time that you're exposed to UV radiation is a good thing, by not being exposed for continuous hours at a time, but short exposure times is the best way to go. And therefore, you're not getting too much exposure, but you're getting enough exposure to get a decent amount of vitamin D. You can also get vitamin D by intaking foods and beverages that are fortified with vitamin D, like most milks and lots of orange juices have vitamin D added to them. So therefore, you can get vitamin D from other sources. And of course, there are vitamin D supplements that you can take as an alternative to obtaining vitamin D from UV radiation. So therefore, how do you know if it's the radiation, the UV radiation outside is at a dangerous level and that you shouldn't be outside, or you shouldn't be outside for long periods of time? Well, there is a UV index forecast that is color coded, and it's used to predict the risk of sunburn from overexposure to sun. So some important factors are the concentration of ozone in the upper atmosphere, what elevation above sea level are you located, and how much cloud cover is there on that given day. So the exposure categories in this UV color-coded index are low, moderate, high, very high, and extreme. And the index numbers range from 0 to 11 plus. So exposure category of low has an index of 0 to 2. And so when the index is reading 0 to 2, if you burn easily, cover up any exposed areas and use sunscreen. Moderate exposure category, if the outside UV index is 3 to 5, stay in the shade when the sun rays are the strongest, like in the middle of the day. And then if it's 6 to 7, the high category, cover up, wear a hat, wear sunglasses, use sunscreen. And therefore, in the hottest, most intense periods of sun rays during the day, which is typically between 10 a.m. and 4 p.m., reduce the amount of time that you're outside during this time period. And then very high, 8 to 10, be especially careful if you're outside, if you're on light colored surfaces like sand or snow or water, as these surfaces are going to be able to reflect the UV radiation, increasing your exposure to it. And so again, minimize your exposure between 10 a.m. and 4 p.m. And then if the index is 11 plus, that means you're in the extreme category. Avoid the sun between 10 and 4. Take full precautions against sunburn and make sure all skin is covered and protected. And so this next picture shows a graphic of our atmosphere, the various layers. Of course, what's shown here is the altitude that each layer is in miles in the red numbers, and in kilometers, the purple numbers. So what that's saying is that the mesosphere starts at 50 kilometers above the Earth's surfaces, which is 31 miles. On the other hand, the stratosphere begins at 15 kilometers or 9.3 miles above the Earth's surface. And so the stratosphere ranges between 15 kilometers to 50 kilometers above the ground. And within the stratosphere, you have this very important layer. There's a very important layer that is within the stratosphere called the ozone layer. It ranges between 15 to 30 kilometers above the ground. So it's in the lower part of the stratosphere. And it's where ozone O3 is in high concentration. And it's the ozone here in the stratosphere, along with O2. So there is O2 here also. It's in the stratosphere where the dangerous UVC radiation is absorbed by the oxygen and the ozone in the ozone layer, and therefore it prevents the dangerous UVC radiation from reaching the troposphere. And so the troposphere, you've got some sea level is of course 0 miles and 0 kilometers above sea level. But then like Denver is about a mile above sea level, which translates to about maybe 2 kilometers above sea level. You can see La Paz, Bolivia is at a much higher elevation. And then of course, Mount Everest, Nepal is almost a whopping 10 kilometers above sea level. Jet airplanes fly at about 12 kilometers above sea level. So that gives you an idea of the high altitude of Mount Everest. And so as you increase your altitude, atmospheric pressure decreases. So there are fewer air molecules at higher elevations. So therefore, it's hard to breathe in higher altitudes. Headaches, tire more easily until your body gets adjusted to that higher altitude. So if you grew up living in areas very close to sea level, and then all of a sudden you move to a higher altitude environment, it may take your body some time to get adjusted to that higher altitude climate. And also one thing to note, water boils at a lower temperature at higher altitudes. So that means the boiling point is less than 100 degrees Celsius at higher altitudes. At sea level, water boils at 100 degrees Celsius, but at higher altitudes, it boils at a little bit less than 100 degrees. So the higher you go in altitude, the lower the boiling point is, or the farther it deviates from 100 degrees Celsius. So talk a little bit more about this ozone layer that's a part of the stratosphere, which protects us from the dangerous UVC radiation. And so the ozone layer has a maximum ozone concentration at about 12,000 parts per billion in the ozone layer. Whereas in the troposphere where we live, the concentration is only about 20 to 100 parts per billion. And in the troposphere, it is an air pollutant. But in the stratosphere, it is a protectant. It protects from UVC in the stratosphere. So that's where we want ozone to be, in the stratosphere. We don't want ozone to be in the troposphere. In the troposphere, it's an air pollutant. And so in the stratosphere, in the ozone layer, you have a high concentration of ozone, but there's also oxygen in the stratosphere. Oxygen has the formula O2, whereas ozone has the formula O3. Ozone is produced from oxygen. So in the stratosphere, oxygen reacts with energy. Where does this energy come from? Electricity. And where does the electricity come from? Lightning. So in the stratosphere, the energy from lightning reacts with oxygen to form ozone. And so this next figure shows us the altitude in kilometers on the y-axis versus the ozone concentration on the x-axis. And so the ozone concentration is increasing as you go from left to right across the x-axis. So in the stratosphere, you have the highest ozone concentration. In the troposphere, you have the lowest ozone concentration. And ozone concentration increases in the troposphere due to air pollution. So that little red spike that you see is due to air pollution. But normally, if there wasn't air pollution, you would have a very, very small amount of ozone in the troposphere. And so ozone concentration is measured in a unit that's called Dobson units. So an ozone concentration, for example, of 300 Dobson units corresponds to compressing ozone at 0 degrees Celsius to form a 3 millimeter thick slab of ozone with a pressure of 1 atmosphere. So that's how they measure ozone concentration in the atmosphere in what are called Dobson units. So now to take a look at some questions. If we wanted to compare oxygen and ozone, they differ in their molecular formulas, but they have the same physical state in the atmosphere. They're both gases. As far as odor, oxygen doesn't have any odor, but ozone has a strong odor. Both are reactive, but ozone is more reactive than oxygen. You have oxygen in the troposphere, of course, and you rarely see ozone in the atmosphere. In the troposphere is part of the atmosphere. When it is present in the troposphere, it is an air pollutant. So in cities that have high air pollution, they'll have ozone. So I checked Chattanooga's air quality index today, and there's no ozone in the atmosphere over Chattanooga today, but there is some PM 2.5, but it's at a good level. It's not at a dangerous level. But then I also checked the air quality index for Denver today, and Denver not only has PM 2.5, but also PM 10 and ozone, but they're all in good quality standards. Then in the troposphere, we have oxygen, and of course we have oxygen also in the stratosphere, but is at a lower concentration than in the troposphere. And do we have ozone in the stratosphere? Yes. And it's at higher concentrations than in the troposphere. And so ozone can absorb UVB and UVC radiation. And so the odor of ozone can be detected at levels as low as 10 parts per billion. So would we be able to smell ozone in either of the following samples of air? If ozone is at 0.118 parts per million, and so we'll take 0.118 parts per million, and we're going to convert it to parts per billion. So we want parts per billion. That goes in the numerator. We want to get rid of parts per million, and therefore that will go in the denominator of our conversion factor. And so we put the numbers that go along with the units. 1 times 10 to the 9th parts per billion per every 1 times 10 to the 6th part per million. The parts per million cancel. We take 0.118 times 1 times 10 to the 9th, and then we divide that product by 1 times 10 to the 6th, and we get 118 parts per billion. So yes, we would be able to smell it because that's greater than 10. So anything greater than 10 parts per billion ozone, we would be able to smell it. And then if we have 25 parts per million of ozone, we're using the same conversion factor as before. And we get a big number, 25,000 parts per billion. So of course, yes, we would be able to smell that ozone as well. The next question, describe 3 differences between the air in the troposphere and the air in the stratosphere. So we can make a little table here to compare and contrast the air in the troposphere versus the air in the stratosphere. The air in the troposphere is more dense than the air in the stratosphere. So the density of air in the troposphere is higher. In the troposphere, we have a lower concentration of both oxygen and ozone. And then a third comparison, the troposphere contains air pollutants. Stuff like So2, NO2, So3, but the stratosphere contains no air pollutants. So when UV light hits ozone, how does ozone absorb that UV light and cause it to decompose and therefore not reach the Earth's surface? Well, it all has to do with the molecular structure of ozone. And so to understand the molecular structure of ozone and other molecules, we draw what are called the Lewis structures for those molecules. So now that we've learned how to name molecular compounds and how to write formulas for molecular compounds, the next step is how to draw the structures for these molecular compounds. So the first thing that we want to understand is the concept of valence electrons. So only a limited number of electrons can reside in the energy levels that orbit around the nucleus. The electrons that reside in the outermost energy levels, which are farther away from the nucleus, they have more freedom of movement. They can jump from one energy level to the next very easily. So those electrons that are in the outermost energy levels, that means it's the farthest away from the nucleus. These are called valence electrons, those that live farthest away from the nucleus. And because they are farthest away from the nucleus, they can therefore be involved in forming the chemical bonds. And so in looking at the periodic table, the group number, for example, group 5A, the group number tells you how many valence electrons that an element has. So all elements in group 5A have 5 valence electrons. And so if we took a look at a picture of the periodic table, I want a more modern one. I want one with the group numbers, the 1A and the versus the 1B and so on and so forth. Nope. These are all the older ones. Nope. Give me 1 second here. I know I've got to have one. Nope. Yes, there we are. So here's a periodic table with the designations 1A, 2A, so on and so forth. So the elements that are in group 1A, those have 1 valence electron. And I abbreviate electron with a lowercase e and a negative superscript sign. And then these in 2A, they have 2 valence electrons. And then jumping over to 3A, 4A, 5A, 6A, 7A, so on and so forth. 7A has 7 valence electrons. 6A, 6. So on and so forth. So the group number tells you how many valence electrons that an element has. So atoms, when they are reacting with each other to form a bond, they're going to react in order to completely fill an outermost level, energy level, with electrons. And so to do this, there must be a total of 8. And so this is called the Octet Rule. The Greek letter prefix OCT stands for 8. And so the Octet Rule says that a stable set of 8 valence electrons is needed in order to make a successful covalent bond. So the electrons get shared between the 2 atoms in order to form this covalent bond. Covalent bonds, of course, are found in molecular compounds. So the covalent bond forms between 2 nonmetal atoms. And so Lewis structures are also called dot structures They are representations of molecules or molecular compounds. And we use these Lewis structures to represent the sharing of electrons between two nonmetal atoms, so that there is a total of 8 valence electrons that both of those atoms that are sharing electrons will collectively possess. So how do we draw Lewis structures? We first want to count up the total number of valence electrons contributed by each atom in the molecule. Then add the valence electrons contributed by each individual atom to obtain the total number of valence electrons that that entire molecule has. Arrange your atoms. You want to place atoms closest to the left bottom of the periodic table in the middle. These atoms that are closest to the left bottom of the periodic table, they are lowest in what's called the electronegativity. So therefore, if we go back to our periodic table, electronegativity increases as we go from left to right across a row in the periodic table. Electronegativity also increases as we go from the bottom to the top of a column in the periodic table. So therefore, fluorine is the most electronegative element of all, because it's closest to the top and farthest to the right. One thing we also want to note is our group 8A, noble gases. They don't have any electronegativity because they don't like to bond with any other elements. They like to exist as free single atoms. They don't want to hook up with any other atom. They don't want to make a bond with any other element. They like being alone. And that's how they exist in the atmosphere, as single atoms, not as molecules. So they have no electronegativity associated with them. They don't like to share electrons. They're selfish. They like to stay alone. They don't want to make a bond. And the reason why is they already have 8 valence electrons. So therefore, they don't need to share. They don't need to borrow or share any electrons from any other atom because they're already happy. Happiness is 8 valence electrons. And so the group 8A noble gases already have 8 valence electrons. So they're happy. They don't need to share electrons with another atom in order to have 8. Neither do they want to give up or share any of their electrons with any other atom that don't have 8. They're selfish that way. And so we're going to place the lowest electronegative element in the middle. And we're going to arrange all the other elements that make up the molecule around that central atom. Now, hydrogen, no matter what, will always be on the outside. Hydrogen will never be the central atom. Then once you've got the least electronegative atom that makes up the molecule in the center and all the other atoms arranged around it, then you're going to place electrons as pairs of dots on the atoms until they meet the octet rule. That means they have 8 electrons around them. So you're going to start on the outside atoms first, placing the dots as pairs. That's why they call them Lewis dot structures, because electrons that are placed around the elements are represented as dots. And you always put the electrons in pairs. Always 2 dots at a time. Hydrogen only needs 2 electrons, period. So if hydrogen is sharing a bond with another element, it's happy. It doesn't need any additional dots around it. It doesn't need 8. It's happy with just 2. So there are elements like hydrogen that violate what's called violate the octet rule. They're happy without having 8 electrons around it. They're happy with just 2. Another element, boron, abbreviated with a capital B, is happy with just having a total of 6 electrons around it. And then another element, beryllium, abbreviated Be, is happy with just having 4 electrons around it. So there are some elements that violate the octet rule. Hydrogen, beryllium, and boron. They are happy with having fewer than 8 electrons around them. All other elements will mostly adhere to the octet rule, meaning that they will want to share electrons with another element or elements until they have a total of 8 electrons around them. And so, if it's necessary, form double bonds to meet the octet rule only after all electrons are assigned. So let's take a look at some molecules and get some practice in drawing Lewis structures. First, we have HCl. HCl is made of 1 hydrogen atom that's in group 1, so there's 1 valence electron. Chlorine, there's 1 of them in the formula, and it's in group 7, so it has 7 valence electrons. So HCl has a total of 8 valence electrons. Hydrogen in group 1A, 1 valence electron. Chlorine in group 7A, 7 valence electrons. 7 plus 1 is 8. So now we draw the Lewis structure. We connect the hydrogen and the chlorine together. That bond represents 2 electrons. So right now I only have 2 electrons in my structure, but I need to show 8 total electrons. And so I place the 8 electrons, or the additional electrons that I need to put in. I've already put in 2, so 8 minus 2 is 6. So I still have 6 left over that I need to put in, and I'm going to put them as pairs of dots around the chlorine. Because remember our rule, hydrogen only needs 2 around it, and there are already 2 electrons around that hydrogen and the bond that it's sharing with the chlorine. So the additional 6 that are needed to be in the structure, I'll put in pairs of 2 dots around the chlorine. So now we've got 2, 4, 6, and 8. So there are your 8 total electrons, 8 valence electrons that need to be in the Lewis structure for HCl. So there is our Lewis structure for HCl. Next, we have Cl2. So we've got 2 chlorines in the formula, and each of them have 7 valence electrons, so that's a total of 14. So we got 2 chlorines. We'll bond them together using a straight line to represent that bond. And again, that bond is 2 of the 14 that we need. So 14 minus 2, that means we've got 12 additional electrons that we've got to put in our structure. So we'll start putting them in pairs of 2 around each chlorine. So that's 2, 4, 6, 8, 10, 12, and 14. And there's our Lewis structure for Cl2. Next, we have water, H2O. Hydrogen is in group 1, and we've got 2 hydrogens in the water molecule, so 2 times 1 is 2. Oxygen, there's 1 of them in the water molecule, and oxygen is in group 6, so 1 times 6 is 6. Add them together, you get a total of 8 valence electrons. And so oxygen will go in the center because hydrogen can never be the central atom. Remember that rule? So since hydrogen can never be in the center, it's always on the outside, I have to put the oxygen in the center and connect the oxygen with the bond to each of the hydrogen atoms. So now I've put in 2 bonds, so that's 4 of the 8 electrons. So I've put in 4 of the 8 required electrons. The remaining 4 I'll put around the oxygen atom in the center, because hydrogen's perfectly happy with just having 2 electrons around it. So those additional 4 electrons will go on the oxygen. And now the oxygen has 2, 4, 6, 8 electrons around it. The hydrogen is happy. Each hydrogen is happy with just having 2 electrons around it. And notice that in the Cl2 molecule, each of the chlorines have 2, 4, 6, 8 electrons around it. 2, 4, 6, and 8 electrons around each chlorine. In the HCl molecule, the chlorine has 2, 4, 6, and 8 electrons around it. Octet rule is satisfied, and of course the hydrogen is happy with just having the 2 electrons around it. Next, we have oxygen O2. There are 2 oxygens in the O2 molecule. Each is in group 6. So 2 times 6 gives us a total of 12 valence electrons. So we'll put the oxygens side by side, connect them with a bond, and that bond is 2 electrons. So that's 2 of the 12 that's needed. And so we'll put the additional 6 electrons around each oxygen in pairs of 2. So 2, 4, 6, 8, 10, 12. But if we call this one oxygen number 1, it's happy. And the reason why I say oxygen 1 is happy is because it's got 2, 4, 6, and 8 electrons around it. But oxygen 2 is not happy because it only has 2, 4, 6 electrons around it. And it needs 8. So therefore, whenever the octet rule is not satisfied for one of the atoms, what you do is erase one of the pairs of electrons around the other atom, one of the other atoms that is happy, and you replace it with a multiple bond between them. So now I've got 2 single bonds between the 2 oxygens. 2 single bonds combined is called a double bond. It equals 4 electrons. Whereas a single bond only has 2 electrons. So now we've got our correct Lewis structure for the oxygen. So there's our correct Lewis structure for oxygen. The next one's nitrogen. It's 2 nitrogens. Each nitrogen is in group 5, so 2 times 5 gives us a total of 10 valence electrons. So I put my 2 nitrogens side by side, and that gives me 2 electrons around each nitrogen. But I need 10 total in my structure. So I'll start adding pairs of dots. So now we got 2, 4, 6, 8, and 10. So nitrogen 1 is happy. It's got 2, 4, 6, 8 electrons around it. However, nitrogen 2 is not happy. It only has 2, 4 electrons around it. So again, just like we did with the oxygen, we're going to take a pair of electrons away from the nitrogen 1 that's happy, and we're going to move those electrons and put them as a single bond, as another single bond between the 2 nitrogens. Now we've got a double bond. But nitrogen 2 is still not happy. Nitrogen 1 is still happy. It has 2, 4, 6, 8 electrons around it. But nitrogen 2 only has 2, 4, 6 electrons around it. So nitrogen 2 is still not happy. So what are we going to do? We're going to take another pair of electrons away from nitrogen 1, which is happy, and move those electrons as another single bond between the 2 nitrogens. And now we've got a triple bond. Between the 2 nitrogens. A triple bond is equal to 6 electrons. So now both nitrogens are happy because they've got 2, 4, 6, 8, 2, 4, 6, 8 electrons around each of them. And there's your correct Lewis structure for nitrogen. And then finally, we've got ozone O3. Each oxygen, there's 3 of them, is in group 6. So 3 times 6 is 18 valence electrons. So we'll put all 3 oxygens next to each other and connect them to each other with a single bond. So I've put in 2 single bonds connecting the 3 oxygens. So those 2 single bonds are 2 electrons each. So I've put in 4 of the 18 required electrons. So now I put in the remaining 18 by putting in dots in pairs of 2 around the oxygens. So I have 2, 4. Now I've got 6, 8, 10, 12, 14, 16, and then the last 2 to give me 18, I'll put her on the central oxygen. So I've got 18 total electrons in my structure now. But now I ask myself the question, are all 3 oxygens happy? Well, oxygen 1 is happy. It's got 2, 4, 6, 8 electrons around it. We'll call this one oxygen 2 and this one oxygen 3. Oxygen 3 is happy. It's got 2, 4, 6, 8 electrons around it. However, oxygen 2 is not happy. It only has 2, 4, 6 electrons around it. So again, to make that middle oxygen 2 happy, we will erase 2 electrons from one of the oxygens that is happy. And it doesn't matter which one I erase electrons from. I can either erase 2 electrons from oxygen 1, or I can erase 2 electrons from oxygen 3. They're both happy, so it doesn't matter which one I take the electrons from. But whichever one I take the electrons from, let's say I'm going to take them from oxygen 1, I took a pair away. I'm going to put that pair in between oxygen 1 and oxygen 2 so that oxygen 1 is still happy. So now I didn't do anything to oxygen 3, so it's still happy. Now oxygen 1 is still happy, but oxygen 2 is also now happy because oxygen 2 has 2, 4, 6, 8 electrons around it. Oxygen 1 still has 2, 4, 6, 8 electrons around it. So now both oxygen 1 and oxygen 2 are happy. So now we've completed our Lewis structure for ozone. So ozone, remember I said that to make the oxygen 2 in the middle happy, I could have taken 2 electrons away from oxygen 1 or oxygen 3. So with some molecules like ozone, they can be drawn with 2 equivalent Lewis structures. These are called resonant structures. So I could have taken 2 electrons away from oxygen 3 and had my double bond on the other side. Remember, this is a double bond shown in purple there. And so my double bond could have been between oxygen 1 and oxygen 2, or it could have been between oxygen 3 and oxygen 2. Both Lewis structures would be considered correct. They are identical Lewis structures, and therefore they are called resonance structures. And the way you draw resonance structures is you put a double-headed arrow between the 2 resonance structures. So here, ozone's resonance structures, the one on the left has a double bond between oxygen 1 and oxygen 2. The one on the right has a double bond between oxygen 2 and oxygen 3. So now in comparing single bonds versus double bonds versus triple bond, you can compare them based on their length and their strength. Bond lengths decrease from single to double to triple. Bond strength increases from single to double to triple. So therefore, a single bond is longer than a double bond, and a double bond is longer than a triple bond. However, a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. And so because ozone has these resonant structures, because this double bond at any time can either be on the right or on the left at any given moment in time, it's said that the double bond and the single bond that makes up the ozone molecule is actually, both of these bonds, the double and the single, have properties that are between that of a single and a double bond. And so it's often called a hybrid bond. A hybrid bond, which is called a 1.5 bond or a 1.5 bond. 1.5 being midway between 1 and 2. So midway between a single and a double bond. And so we said that ozone ozone has the ability to absorb UVC and UVB radiation, but only UVC is strong enough to break the double bond in oxygen. So oxygen's Lewis structure, as we recall, consists of one double bond, whereas ozone O3 consists of a single bond and a double bond, which we say is really a hybrid bond. And so therefore, we can define what's called bond order, which is related to bond strength. So we got 4 types: the single, the double, and then the hybrid that falls between a single and a double, and then the triple. So a single bond order is 1, a hybrid's bond order is 1.5, double is 2, triple is 3. So therefore, oxygen has a double bond, whereas ozone has 2 hybrid bonds. So therefore, that double bond in oxygen has a bond order of 2, whereas the hybrid bonds in ozone have a bond order of 1.5. So therefore, UVB is capable of breaking the bonds in ozone to form atomic oxygen and the oxygen molecule O2, whereas it takes the stronger UV radiation to break the double bond in oxygen to form 2 atomic oxygen atoms. And these 2 oxygen atoms, they get fed into what's called the Chapman cycle. The Chapman cycle is a set of reactions, which we call a reaction mechanism, that occur naturally in the upper atmosphere, which we call, of course, the stratosphere and the ozone layer. And what these set of reactions do is result in a steady state concentration of ozone in the stratosphere, so that we've always got enough ozone there to block the dangerous UVC radiation from reaching the troposphere, because that dangerous UVC radiation gets used up or absorbed by the ozone in the ozone layer of the stratosphere. So once oxygen's double bond gets broken by UVC radiation, you get your 2 atomic oxygen atoms. And they get fed into the Chapman cycle by reacting with oxygen, and it collides and reacts fast with oxygen to form ozone. And then the ozone can break down into oxygen and atomic oxygen, O2 and atomic oxygen. And then the ozone can also go on and react with atomic oxygen, but it does so in a slow manner to form more oxygen. And that oxygen goes on and gets recycled and starts the process all over again. So it's a cycle. It happens over and over again so that you maintain this steady amount or steady concentration of ozone in the stratosphere. So taking a look at some questions. Indicate the number of valence electrons for each of the following elements. Well, that depends on the group number. So magnesium is in group 2A. So it has 2 valence electrons. Sulfur is in group 6A, so it has 6. Bromine is in group 7A, so it has 7. Nitrogen is in group 5A, so it has 5. And carbon is in group 4A, so carbon has 4 valence electrons. And so we have some more Lewis structures to practice drawing. And so bromine, Br2. Each bromine is in group 7, so that's 14 valence electrons. So bromine, Br2, its Lewis structure is going to look very similar to that we drew previously for Cl2 because they're in the same group. They have similar properties, and one of those are they have similar looking Lewis structures. H2S contains 2 hydrogen atoms, each in group 1A. Sulfur, there's one of them, and it's in group 6. So H2S is going to look a lot like H2O. Oxygen and sulfur are both in group 6A. So H2O and H2S, their Lewis structure should look similar. We already drew the Lewis structure for H2O, so that for H2S should look the same. All you do is replace the O with an S. And there are your 8 valence electrons. 2, 4, 6, 7, and 8. CCl2F2, you got 1 carbon in group 4, 2 chlorines, each in group 7, 2 fluorines, each in group 7. That's a total of 32 valence electrons. And so carbon is the least electronegative of these two. Carbon is farther to the left than fluorine and chlorine, and electronegativity increases as you go farther to the right. So therefore, carbon is going to be the central atom because it's the least electronegative. And we're going to connect via single bonds, each chlorine and each fluorine to the central carbon. So we need to put in 32 valence electrons. We've already put in 2, 4, 6, and 8. 32 minus 8 is 24. So we need to put in the remaining 24 as pairs of dots around around the outer atoms. The outer atoms in most textbooks are called peripheral atoms. And sometimes you'll just see them referred to as outside atoms versus the central atom. But I like to call them peripheral atoms. So now I've put in my additional 24, putting 6 electrons around each of the 4 peripheral atoms, 6 times 4 being 24. And then I've got the 8 represented here as bonding, single bonds, bonding the central atom to the peripheral atoms, giving us a total of 32. Note that all of the atoms are happy. They all have 8 electrons around them. And the same is true for the 2 bromines. The sulfur has 2, 4, 6, 8 electrons around it. And remember, hydrogens are happy, just having 2 electrons around them. Next, we have carbon monoxide, CO. Carbon, there's 1 of them in group 4. And there's 1 oxygen, which resides in group 6. And so that's 10 valence electrons total. We put the carbon and the oxygen next to each other, bonding them with a single bond. So we've already put in 2 of the 10. So we have 8 remaining. So 2, 4, 6, and 8. So we've got a total of 2, 4, 6, 8, 10. The carbon is happy, having 2, 4, 6, 8 electrons around it. But the oxygen is not happy because it only has 2, 4 around it. So again, we follow our rule. Whenever one atom is not happy, meaning it doesn't have 8 electrons around it, we remove a pair from the atom that is happy, and then we move that pair of electrons so that it's between both of the atoms, and now we've made a double bond. But the oxygen is still not happy because it only has 2, 4, 6 around it instead of 8. So what do? We take another pair away from the carbon, which is happy, and then we put another single bond between the carbon and the oxygen, making a triple bond. Now both the carbon and oxygen are happy because they have 2, 4, 6, 8, 2, 4, 6, 8 around them. And there's the correct Lewis structure for carbon monoxide, CO. Now, in our physical and chemical changes lab, we saw a reaction that was the elephant toothpaste reaction, in which we observed the decomposition of hydrogen peroxide. That's what this is, H2O2. That's hydrogen peroxide. And we needed that sodium iodide catalyst to actually see the decomposition of ozone. I'm sorry, the decomposition of H2O2. And so H2O2 has 2 hydrogens, each in group 1, and it has 2 oxygens, each in group 6, giving us a total of 14 valence electrons. So we'll put the oxygens in the center because the hydrogen can never be in the center. Hydrogen always has to be on the outside. So I've connected the hydrogens and oxygens together using 3 single bonds, each with 2 electrons. So I've put in 6 of my required 14. Hydrogen's happy with just having 2 around it. So the remaining electrons that I need to put in are 8, and I'm going to put those around 2, 4, 6, 8 around the oxygens. Now the oxygens are happy. They have 2, 4, 6, 8, 2, 4, 6, 8 electrons around them. So the oxygens are happy. They have 8 electrons around them. And the hydrogens are happy with just having 2 electrons around them. Next, we have N2O, 2 nitrogens, each in group 5, 1 oxygen in group 6. So 16 total valence electrons. And so with this one, we're going to let one of the nitrogens be the central atom because nitrogen is less electronegative than oxygen. And then one of the oxygens will be on the outside, and the oxygen is going to be on the outside. So we've put in 2, 4 electrons already with the 2 single bonds. So now we'll use our pairs of dots because we've got to put in 12 additional. So 2, 4, 6, 8, 10, and 12. And then 14 and 16. So we've got our 16 electrons in there. Nitrogen 1 is happy. It's got 2, 4, 6, 8 electrons around it. But nitrogen 2 is unhappy. Nitrogen 2 only has 2, 4 electrons around it. The oxygen is happy. It has 2, 4, 6, 8 electrons around it. But the central nitrogen is unhappy. So we're going to move 2 electrons from one of the elements that are happy. The outside nitrogen is happy. So we're going to take those electrons and we're going to move them so that they are between the 2 nitrogens. Nitrogen 1 is still happy. 2, 4, 6, 8. But nitrogen 2 is still unhappy because it only has 2, 4, 6 around it. So what we're going to do then is move another pair of electrons, this time away from the oxygen, and we're going to put that pair of electrons as a single bond between the nitrogen, the central nitrogen, and the oxygen. Now the nitrogen 2, the central nitrogen, is happy, and so are the outer nitrogen and the oxygen. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So our correct Lewis structure and of course, there's a resonant structure. We could have taken another pair of electrons away from the outer nitrogen and therefore had a triple bond between the outer nitrogen and the central nitrogen and kept the single bond between the central nitrogen and the oxygen. So both of these are considered correct. So these are resonance structures. Next, we have SO2 and SO3. So SO2, there's one of them in the formula in group 6. We got 2 oxygens also in group 6. So that gives us 18 total valence electrons. Whereas SO3, again, 1 oxygen in group 6, but 3 oxygens in group 6. So that gives us 24 total valence electrons. So for SO2, we got sulfur connecting to 2 oxygens. And so we've put in 4 of the required 18 already. 2 and 4. And now we need an additional 18 minus 4 is 14. So put in another 14. So 2, 4, 6, 8, 10, 12, and then the last pair will go on top of the central sulfur. So the 2 oxygens are happy, but the sulfur is not happy because it only has 2, 4, 6 electrons around it. So again, we follow our rule. We take a pair of electrons away from one of the outer atoms that are happy, and then we move that pair and put a single bond between that outer atom and the central atom. Now the sulfur is happy. But we also could have taken the pair away from the other oxygen and had the double bond between the sulfur and the oxygen number 2. So these are resonant structures. And to indicate resonant structures, again, you draw a double-headed arrow between the 2 structures. And we can also consider, like we said, this a hybrid bond. And you indicate the hybrid by having a dashed line and a solid line. The dashed line represents a half of a bond. The solid line represents a entire whole single bond. And so this is the hybrid resonance structure, showing the hybrid 1.5 bond. So the bond order equals 1.5 for each of those bonds. So that's SO2. Now for SO3, we've got a sulfur in the center connected to 3 oxygen atoms. And so we've put in 2, 4, 6 of the required 24 valence electrons. So we need to put in 18 more. 6 plus 18 is 24. We've already got 6, so now we need the 18. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. All 3 oxygens are happy. They've got 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8 electrons around them. But the sulfur is unhappy. The sulfur is unhappy because it only has 2, 4, 6 electrons around it. So to relieve its unhappiness, we're going to remove a pair of electrons from one of the happy oxygens and replace those 2 electrons that we removed as a single bond between the oxygen and the sulfur, giving us a double bond. And so now the sulfur has 8 electrons around it and it's happy. But we could have taken the 2 from either oxygen 1 like we did, or we could have taken the 2 electrons from oxygens 2 or 3. And so we can draw resonant structures. So if we would have taken the electrons from oxygen 2, our double bond would have been between the sulfur and oxygen 2. Or we could have taken the oxygen, the electrons from the oxygen number 3. And therefore draw another resonant structure with the double bond between the sulfur and oxygen 3. And so this is also a correct structure. So for SO3, we can actually draw 3 resonant structures. So around the central sulfur atom in SO3, these bonds, the single bonds and the double bond, these are called bonding groups. So the central sulfur atom has 3 bonding groups, 2 single bonds and 1 double bond, and 0 non-bonding groups. Now comparing that to SO2's resonant structures, this central sulfur also has some bonding groups, but it only has two bonding groups, the double and the single. But it also has a non-bonding group, the lone pair of electrons, one bonding group, one non-bonding group. So that's called a lone pair of electrons that's just sitting on that central sulfur atom. It's not being bonded to another atom. So it's called a non-bonding group. But the single and the triple bonds, those are your two bonding groups around that central sulfur. And so that brings us to the end of part 2 of the chapter 3 pre-class lecture.